almost 2 times the height of the Eiffel Tower, exactly the vertical scale required to drive through the clouds on the Huajiang Bridge. 625 meters of altitude separate the deck from the water level, securing its title as the highest bridge in the world. Inaugurated in September 2025, the structure quickly became a new icon of industrial capability. One can notice how the road surface seems to dissolve into the mist, suspended above the abyss. But this is just the beginning. The location presents a deadly challenge to any machinery. Why did engineers decide to stretch this colossus through the most insidious hills in western China? At first glance, the rough terrain and dense layers of snow appear impenetrable to construction teams. However, conquering this geography was essential, even after many previous projects were abandoned long before the work could be completed. It seems like fiction to place a bright bar right on top of the tower, but in reality, this architectural feature exists vividly between the clouds. The structure challenges the elements, standing firm where others failed. One can see the contrast between the advanced materials and the wild, frozen landscape. It gets more complex further on. The process combines Amandla and tech to reveal how Chinese engineers transform this bold project into reality. Thus, the engineering feat moves from a plan to a solid reality above the skyline. 92% of the entire surface of the province of Guo consists of impenetrable high mountains and high plains. 8 large rivers and countless affluents form deep valleys in this harsh region, making transport and trade a constant challenge. One can notice how the jagged terrain cuts off access to the outside world, isolating the area. Therefore, the journey of this bridge of records began in one of the most harsh regions of all China. The Oiji-Anlong Highway, which connects the Opens with the Anlong County, had to conquer this landscape to succeed. The route was forced to pass through the dangerous crossroads of the Baiyuan River inside the Gola of Huajiang. Why was the Huajiang Bridge created in such a specific spot? During the phase of investigation, engineers found themselves faced with 2 options with similar costs. One was to build a pleasant access road, but to place the bridge near the top of the mountain, while the second option was to build the bridge below, but to pass it through a series of steep and long galleries. In the end, they chose the challenge of about 250 feet to minimize the impact on the impervious territory. A V-shaped gorge created a distance of over 4,000 feet, equivalent to more than 1,400 meters between the 2 edges of the rock. The camera glides along the steep cliffs, emphasizing the sheer scale of the emptiness where the structure must stand. In these dimensions, all other types of bridges have failed to provide a solution. The bridge with the most rigid trunks in the world could not have covered that distance, and the bridge with the longest arch could not have reached the other side. Even the largest suspension bridge would not have been able to cross the camp effectively. But this is just the beginning of the engineering puzzle. Only a bridge suspended with a main overhang would have been able to satisfy these extremely severe engineering requirements. At first glance, the solution seems simple, but in reality, the logistics are a nightmare. Builders start the process by constructing 2 massive towers on the opposing cliffs. Then, they put the 2 main cables in position and fix them tightly to bear the weight. Finally, the bridge is hung using the suspension cables, completing the basic form. However, this is just theory. Everything is much more complex because the Huajiang Bridge is 625 meters above the river. With a 1,400-meter-long canyon across the canyon, the scale is unprecedented. If its tower structures are included, the bridge is comparable in height to the tallest artificial building in the world. It is visible how the steel components hang suspended against the backdrop of the sky. Consequently, it is clear that the Huajiang Bridge is not only imposing on paper, but requires a construction process that goes beyond the standards of normal infrastructure projects. 24 huge concrete slabs form the hidden anchor of this massive infrastructure project. Why did the foundations of the bridge tower require such a complex system of drilling and qualification? To the untrained eye, the ground appears solid enough to support the structure. But the geological reality presented layers of rock and rows full of cracks and aquifer faults, where even the smallest error could cause serious accidents. Engineers drilled deep into the earth, utilizing a special system of palification to navigate the strata. One can notice how the equipment carefully maneuvers to avoid disturbing the water tables. But this is just the beginning. At first glance, this appears to be a routine pour. But in reality, it is a specialized operation ensuring long-term survival. The system combines the slabs in depth in the ground with reinforcement in anti-seismic steel. This creates a matrix robust enough so that the Dora can resist decades of operation. One can observe the steel bars locking into place within the excavated shafts. The foundation work concludes here, allowing the structure to rise safely. 262 meters. This is the precise height of the primary column erected after the foundation challenges are overcome. The second main tower reaches 205 meters, serving as an anchor point for the entire system of cableways. Why build them directly on the side of the mountain? At first glance, placing such mass hundreds of meters above the gorge seems risky for the structure's integrity. But in reality, this positioning provides the essential geometric elevation to span the void. Construction teams ensure the tower could resist decades of operation. One can notice how two huge weight cables, weighing over 9,000 tons each, descend from these summits. The load is immense. These towers support the bridge like two giant pillars that hold a tape in the middle. Because stability is fundamental, the framework is fortified with high-resistance steel. But this is just the beginning. The design must be able to withstand strong winds, vibrations, and even earthquakes for its entire design duration. It is visible how the reinforced core stiffens the columns against the harsh elements. Thus, the towers stand rigid, ready to accept the suspended load. 164,000 cubic meters of limestone form a block of extremely stable resistance on the Yanfang side. This massive gravity anchor rests solidly on the mountainside, ensuring the structure withstands even earthquakes for its entire design duration. One can notice how the huge towers rely on this foundation to really exercise their strength. But this is just the beginning of the engineering solution. The cable anchor system must be sufficiently robust to keep the entire structure in place. Why was the anchorage on the Guanling side designed differently as a tunnel of anchorage? The geography presents a stark contrast to the Yanfang side. Behind the tower on the Guanling side, there is a steep mountain, but the amount of land available behind it is extremely limited. Instead of positioning a massive block of limestone on the surface, engineers took a more invasive approach. They dug in depth into the other side of the mountain to fix the anchorage system directly to the natural rock. At first glance, digging tunnels seems like an unnecessary complication, but in reality, it allows the transfer of the entire tension of the cables into the mountain itself. It is visible how the natural rock formation acts as the primary stabilizer. The process is only gaining momentum. Using the mountain itself as a natural anchorage has therefore become the optimal solution. The Huang Bridge anchors work as gigantic counterweights that solidly block the two main cables in the mountains. This choice saves space while simultaneously increasing the stability of the entire structural system. The engineering design guarantees that the bridge remains immovable regardless of external forces. Thousands of meters separate the towers after the anchorage blocks are complete. A temporary walkway is suspended here for operators to build the cables. One can notice the sheer drop below the structure, but this is just the beginning. Why use drones to pull the first pilot line? The deep throat is too vast for manual lines. It is visible how engineers use drones to drive the cables. making the task safer and more precise. At first glance, the line seems simple, but in reality, it is vital. Once pulled, the walkway is raised. The equipment gradually secures the platform for the biocritical phase. The construction of the two main cables follows. Tens of thousands of high-resistance steel wires intertwine with absolute precision to form the backbone. This marked the next step and the most important phase of the entire Rava Trent project, the construction of the two main cables. Effectively, the main cable is the main bridge, capable of holding tens of thousands of tons of load. Why is such extreme scrutiny applied on the half-air suspension footbridge? It seems the scale would allow for deviations, but without precision, the integrity of the span is lost. Each cable strip consists of 91 steel wires with high resistance and a diameter of 5.7 millimeters. Workers pull them forward and backward between the anchor points ceaselessly. One can notice how the metal strands accumulate. Superficially simple, the installation faces the challenge of strong winds at an altitude of thousands of feet. But in reality, the supervision of the global positioning system ensures the alignment remains perfect. This technology allows engineers to maintain a lower error of less than 2 millimeters. The control of every movement of every turn was of fundamental importance. It gets more complex further on. A cable fixing machine finally engages the metal bundle. Once all the 200 of the certain turns are installed, the device compresses and connects the cables into a circular cable using a special process of fitting. It is visible how the machine binds the structure. After that, the cable has been wrapped in several protective layers to resist corrosion, colds, and vibrations for decades. Only when these two huge main cables have been completed can the work advance. The bridge has been able to move on to the next phase, suspending the deck of the bridge in mid-air. 2,000 feet above the water is the altitude where the decisive phase of construction takes place. Once the two main cables were completed, the bridge went to the critical stage of suspending the deck in mid-air. First, the engineers installed the vertical slat system, each fixed to the main cable using special slats capable of resisting thousands of tons of force. These components transfer the load from the floor of the bridge to the main cables and then distribute it to the two anchor points. But this is just the beginning. Why is the entire bridge made up of 93 steel segments lifted starting from the center? It would seem logical to start construction from the banks. However, the segments are lifted one by one from the middle and gradually extended to the outside on both sides. One can notice how each segment, weighing hundreds of tons, is welded using a system of slats suspended in the sky. At first glance, this assembly looks straightforward, but in reality, the tension in the slats requires constant monitoring. Engineers control the position of each panel to ensure that the entire floor remains aligned without tilting or twisting under the forces of the wind. The process is only gaining momentum. Once positioned and connected in a unified structure, the upper floor system is then built. All 93 segments effectively transform the suspended steel structure into a completely functional highway. 96 heavy trucks, exactly the fleet used to evaluate the actual resistance of the bridge once construction finalized. In August 2025, these vehicles, with a total weight of 3,700 tons, tested the carrying capacity and performance. One can notice the heavy tires pressing firmly onto the fresh asphalt. But this is just the beginning. Why apply such massive pressure immediately? It seems excessive to burden a new structure, yet this load is necessary to ensure the bridge meets the most severe safety standards. It is visible how the technology tracks the impact. Over 400 sensors record precise data on deformation, oscillation, and vibration. At first glance, the deck appears static, but in reality, innovations in structural monitoring capture every micro shift in real time. Therefore, the test confirms absolute safety. The sensors stabilize as the evaluation proves the engineering quality. The bridge is ready for the next phase, level 14. On the Beaufort scale is the extreme intensity the wind can reach in the Gola of Huajiang during favorable seasons. During the construction of the highest bridge in the world, the construction team has constantly had to face extremely difficult challenges from both nature and the ground. Why must construction be interrupted every time the winds reach level 6 or higher? The difference between the recorded peak and the safety limit seems vast. This strict protocol is necessary to ensure the safety of the workers against the unpredictable gusts. The transport of steel beams into the installation position demands absolute precision. At first glance, the process appears to be a standard mechanical operation, but in reality, the stabilizing supports sometimes crumbled under the stress, forcing workers to straighten them manually. One can notice how the team maintained the lines in equilibrium between the sides of the mountain and the valley to reduce the minimum risk of torsion. They started working at 6 in the morning and often did not return before sunset. It gets more complex further on. 439,000 cubic meters of limestone were required for the Eiffel Bridge. This total volume is the equivalent of 176 Olympic swimming pools. To reduce costs and protect the environment, engineers reuse the waste rock produced during construction. Giant crushers break the debris into high-performance green mineral powder, and it is visible how this material is used to replace 20% of the cement in every cubic meter of limestone. Consequently, this approach not only allows the team to save cement, but also fully exploits the waste rock to limit pollution. The construction team has thus overcome the natural challenges, delivering the project in a sustainable and efficient way. 1.5 hours is the maximum time required to travel from the bridge area to the city of Guang today. Previously, this journey took at least 3 hours, consuming valuable resources and limiting mobility. The opening of the bridge saves almost half the travel time for every vehicle crossing the span. This acceleration not only makes life more comfortable for local residents, but also benefits thousands of other people operating in the area. Why was the Huajiang Bridge designed as a dual-purpose structure from the very beginning? The engineering plan required a solution that addressed multiple needs simultaneously. At first glance, it seems like a standard engineering solution to cross the canyon. But in reality, the design ensures both structural integrity and the experience of visitors. This approach allows the bridge to function simultaneously as a transport link and a high-altitude tourism destination. One can notice how the structure integrates wide views and ideal elevations into the engineering framework. Both sides of the bridge have been equipped with safety rings and a specialized road coating. This surface layer stabilizes the bridge against environmental factors while simultaneously supporting high-quality adventure sports. Inside the steel cross, there is a walkway for visitors. Otherwise, this path would simply serve as a maintenance passage for engineers. But this is just the beginning. The impact extends far beyond what is visible to the naked eye. It reshapes the economic landscape of the entire zone. By connecting to the G56 Superway, the bridge opens up regional commercial routes between China and Southeast Asia. This reduction in travel times attracts investments and creates jobs. Access to healthcare improves significantly for remote communities. Tourism brings the entire region closer to a prosperous future. The infrastructure is ready for the next phase of operation. Thousands of separate engineering tasks were executed to finalize the impressive structure of the Huajiang Bridge. Why was absolute precision required from the very first days of deep drilling in the rocky road? The project seemed to grow day after day from a schematic idea on paper into a massive physical form. This exactness ensured that the cement for the tower's beams and the main completion of the peaks could withstand the calculated loads. But this is just the beginning of the technical complexity. The installation of steel transversal rails follows the establishment of the primary supports. One can notice how the heavy suspension cables stretch taut during the critical tensioning process. Every locking component is assembled with zero tolerance for error to secure the connections. It is visible how the bridge finally crosses the deep canyon, turning into a masterful reality. At first glance, the structure looks like a static monument, but in reality, it is the culmination of the intelligence and perseverance of Chinese engineers. The history of the Huajiang Bridge is not only the history of a world record, but a testimony to the transformation of the Guizhou province. From a remote land to a harsh one, the region is now integrated into the modern rhythm of the 21st century. And this is not the limit of human capability. Imagination and perseverance continue to give life to mechanical wonders and extraordinary technological discoveries that are considered impossible.